Hi, this is Physics 503, Nuclear Physics, and in this lesson we're going to discuss about your major decay modes, your alpha, your beta, and your gamma decay. The three common decay modes of the nuclei, your alpha, beta, and gamma, were all observed by the early 20th century. When a nucleus decays, all the conservation laws must be observed, including your mass energy conservation, your linear momentum conservation, your angular momentum conservation, and your conservation of electric charge. To these laws, we add another one for the radioactive decay, which we will call as the conservation of nucleons. In the conservation of nucleons, it states that the total number of nucleons A, here the mass number, must be conserved in a low-energy nuclear reaction or decay. Neutrons may be converted into protons and vice versa, but the total number of nucleons must remain constant. Radioactive decay may occur for a nucleus when some other combination of the A nucleons has a lower mass. Here we let the radioactive nucleus X be called the parent, and let's say it has a mass of M of X, and two or more products can be produced in this decay. In the case of two products, let the mass of the lighter one be My, and the mass of the heavier one, which we normally call as the daughter, be Md. The conservation of energy then becomes your M of X that's equal to the mass of the heavier one plus the mass of the lighter one plus your Q over your C squared. Here, your Q is the energy release, or we also call this one as your disintegration energy, and this is equal to the total kinetic energy of the reaction of products. Your Q is equal to your mass of your nucleus minus the mass of the daughter, and then the mass of the lighter one times this whole quantity is multiplied by your C squared. If you see, the disintegration energy Q is just the negative of the binding energy B. And the binding energy normally refers to the stable nuclei, whereas Q is normally used with unstable nuclei. Again, the binding energy B here, we usually refer for we usually use this one to refer for the stable nuclei, whereas your Q is for an unstable nuclei. If B is greater than 0, a nuclide is bound and stable. If Q is greater than 0, a nuclide is unbound, unstable, and may decay. If, on the other hand, Q is less than 0 or a negative, it decay, or the decay-emitting nucleons do not occur. If nucleon decay were possible for this radioactive nuclei, it would have taken place too quickly for the nuclei to be naturally abundant. This is for the case when your Q is less than 0. Now let's talk about the alpha decay and consider the nucleus of your helium-4. The nucleus of helium-4 has a binding energy of around 28.3 megaelectron volts. And if the last two protons and two neutrons in the nucleus are bound by less than this one, by less than 28.3 megaelectron volt, then the emission of an alpha particle or alpha decay is possible. Your For the alpha decay, the equation is you have your X, which decays to your daughter nuclei, plus your alpha particle. Here, your Q, your disintegration energy, for example, in the helium-4 is just your M of X minus M of the daughter nuclei minus the mass of your helium-4 times C squared. If Q is greater than 0, then the alpha decay of helium-4 is possible. If you get here a Q that's a negative, then the alpha decay is not possible for this case. Again, you have here the equation for your of your alpha decay. In your alpha decay, again, you have the emission of your alpha particles. And if you have here your parent nucleus, it emits or it decays into a daughter nucleus, and then it also emits uh, an alpha particle. And in the alpha decay, the atomic number decreases by 2 and its atomic mass decreases by 4. A simpler equation for your alpha decay is represented by this one here. Here you have your parent nucleus, which decays into your daughter. Here your A decreases by 4, and then your Z decreases by 2, and then it emits your alpha particle, which in this case you have your helium-4. Your helium-4 here is just your alpha particle. So you can use this equation here later to balance equations or to derive the alpha decay mode of your many unstable nuclides. Now let's consider the nucleus of your uranium-230, which has a an atomic number of 92. And let's look at the alpha decay reaction. The alpha decay reaction is given by your parent nuclei, your uranium-230. So we subtract 4 to the atomic mass. So you have 230 minus 4, so it becomes 226. And then 92 minus 2, so you have 90. And we look at an element which has an atomic number of 90. And from the table of elements, you see that this is thorium. So your uranium-230 decays into thorium-226, and then it also emits your alpha particle, where in this case here you have your helium-4. And this is the alpha decay reaction, but we still need to look at your Q to say or to verify that the alpha decay is allowed. And we look for the appropriate masses to find your Q. And these are your mass of your uranium-230, and then the mass of your helium-4, then the mass of your thorium-226, and we use these values here to solve for Q, and we find that your Q is equal to 6 mega electron volts. Here, because Q is greater than 0, then your alpha decay is allowed. Many of the nuclei above A150, in fact, are susceptible to alpha decay. These heavy column nuclei have increasingly stronger column repulsions as more protons are added. And in order for your unstable nuclei to be more stable, the expulsion of 2 protons along with 2 neutrons in the form of alpha particle may decrease this column energy and make the resulting nucleus more stable. And that is what happens inside your alpha decay mode. Next, let's talk about the beta decay. Unstable nuclei may move closer to the line of stability in your Segre chart by undergoing your beta decay. And the simplest example of your beta decay is the decay of your free neutron, where here you have your neutron that decays into a proton plus your beta minus particle. Now we know that your beta particle, your negative beta particle, or your beta minus particle, this particle is just actually your electron. And this is created at the time of decay. For example, the beta decay of your carbon-14, which is an unstable atom to form your nitrogen-14, a stable nucleus, can be written as the following using your free neutron decay. So you have carbon-14 that decays to nitrogen-14 and it emits a beta minus particle. And this decay produces 2 products, just like your alpha decay, and we expect to measure a monoenergetic electron spectrum. However, as you can see here in the figure, the electron energy spectrum from the beta decay of carbon-14 shows a continuous energy spectrum up to some maximum energy. And this experimental result was actually a major puzzle for many years. There was also a problem with your conservation of your spins or your spin conservation. In the neutron decay shown earlier, the spin 1/2 neutron cannot decay to spin 1/2 particles, a proton and an electron. Also, your carbon-14, which has a spin of 0, Your nitrogen 14 has a spin of 1 and the electron has a spin of 1 half. We cannot combine the spin 1 half and 1 to obtain a spin 0, as you can see. Both the electron energy spectrum and then the spin angular momentum conservation pose major difficulties with our understanding of the beta decay. And it was Wolfgang Pauli who suggested that a neutrino, nu, must also be produced in the beta decay. The neutrino with a symbol of nu has spin quantum number 1 half, charge 0, and carries away the additional energy missing. Just a little about your neutrino. Your neutrinos interact weakly with matter that they pass right through the Earth with little chance of being absorbed. Neutrinos have no charge and do not interact electromagnetically. They are not affected by the strong force of the nucleus. And we now believe that the beta decay is actually a reflection of the weak interaction force. The electromagnetic and then the weak forces in general is called the electroweak force. So these are some details about your neutrino. Let's discuss the first type of your beta decay, your beta minus decay. And we now know that there are antineutrinos. Here, your antineutrinos has a symbol of nu bar. And uh, the beta decay of a free neutron of carbon-14 is now correctly written as your neutron that decays into a proton plus your beta minus plus your nu bar. This is now the corrected form of your beta minus decay. And for the free neutron of your carbon-14 decays into nitrogen 14 plus your beta minus plus your nu bar or your antineutrino. In the general beta decay of the parent nuclide X to the daughter nuclide D, the reaction is given by this equation. You have your parent X, which decays into the daughter D, plus your beta minus plus your nu bar. Here, in your daughter, the nucleus A is constant, but Z charges to Z plus 1. And the disintegration energy Q is given by this equation here. This is for your beta decay. In order for beta minus decay to occur, we must have your Q that is greater than 0 or a Q that is positive. Otherwise, if you get a negative Q, then the beta decay of the nucleus that you are thinking about may not be possible. So we have here the diagram of your or the figure of your the beta minus decay of your free neutron carbon 14 into nitrogen 14. So it emits two particles. You have your antineutrino and then your electron. Or again, this is just your beta minus particle. And in your beta minus decay, the emission of beta particles are identical to electrons originating from the nucleus. In your beta decay, your beta minus decay occurs when a neutron is changed to a proton within the nucleus. And this is again the form of your beta minus decay. So your N decays into a proton or changes into a proton, emits your beta minus, your electron, plus your antineutrino. And you can use this formula here in order to write the equation for your beta minus decay. So you have your P, AZ, which decays to D, A, the same A, while your Z charges to 1, so Z plus 1, plus your electron, so and then plus your antineutrino. So you can use this one later in exercises in forming your beta decay equations for your unstable nuclides. You may actually ask what happens for an unstable nuclide or for unstable nuclides with too many protons. Nature does allow such a transition, and in such cases, a positive electron, which we call as your positron, is produced. So it's a plus E, so a positively charged electron. So the positron is the antiparticle of your electron. In beta decay, the electron and positron are normally referred to as your beta minus and then your beta plus decay respectively. So that's why it's called your beta minus, because it produces or it emits an electron. It's a beta plus decay because it emits a positron. Current experimental evidence indicates that a free proton does not decay when its half-life is greater than 10 to the 34 years. But a proton bound within the nucleus may transmute if energy is taken from the nucleus and the result is a more stable nucleus. For example, you have the nucleus of your oxygen 14, which is unstable, and it decays by emitting a positron to become a stable nitrogen 14. So here you have, for example, your oxygen 14, which decays to nitrogen 14. It emits your positron and then your neutrino. So this is your beta plus decay. The general beta plus decay form is given by this equation here. You have your parent X decays to your daughter D. Here your A is constant, but your Z, uh, you have your Z minus 1 plus your beta plus, and then, or your positron plus your neutrino nu. The disintegration energy, on the other hand, of your beta plus decay is given by this equation here. In your beta plus decay, for example, in your carbon 10, uh, your carbon 10 decays to boron 10, it emits a neutrino and then it also emits a positron. So you have the emission of protons, which is an antiparticle of electron, and it occurs when a proton is changed to a neutron within the nucleus. So what you see now here in your beta plus decay is that you have your proton, it decays to a neutron, and it emits your positron, your beta plus particle, plus your neutrino nu. You can also use this equation here, okay, to find the beta plus decay equations of your unstable nuclides. So you have your parent P, which decays to your daughter D. A is constant, so and you have Z minus 1 plus uh, your positron, and then plus your neutrino nu. So you can use this one here later in in finding the equation for your beta plus decay. There is one other form of your beta decay, and we call this one as your electron capture. Classically, because your inner H shell and then your L shell electrons are tightly bound and their classical orbits are highly elliptical, these electrons spend a reasonable amount of time passing around or passing through the nucleus, thereby increasing the possibility of atomic electron capture of your electron into the nucleus. A proton in the nucleus absorbs your electron. Again, a proton in the nucleus absorbs the electron, producing a neutron and a neutrino. The reaction for the proton in the electron capture is you have your P plus your proton plus your electron. It produces a neutron N plus your neutrino. The general reaction for your electron capture is given by this equation here. You have your parent plus your electron, the captured electron, which then decays to a daughter, and then plus your neutrino. So here you have still the same number of A, but your Z, you subtract 1 to your Z. This is for, again, for your electron capture. And the disintegration energy, Q, is given by this equation here. For example, you have the electron capture of your electron in your carbon 11. So your carbon 11 has 6 protons and 5 neutrons. It captures an electron and then it becomes boron 11, which has 5 protons and 6 neutrons. And it also produces your neutrino. So your carbon 11 captures an electron to be more stable carbon 11. A proton-rich nucleus captures an inner shell orbital electron, usually in the K shell, transform a proton into a neutron and ejects a neutrino. So this is again for your electron capture. And electron capture will be followed by the emission of a characteristic photon or OG electron. So this is the equation which you can use for your electron capture. So you have your parent nucleus plus your electron, your captured electron, and it transform into a daughter nucleus plus your neutrino. Lastly, let's talk about your gamma decay. So a nucleus has excited states in much the same way atoms do. The excitation energies tend to be much larger in many kilo electron volts or me, uh, mega electron volts as a result of a stronger nuclear interaction. One of the possibilities for the nucleus to rid itself of this extra energy is to emit a photon, which is a gamma ray, and undergo a transition to some lower energy state. The decay of the excited state of your X, where you have here your star, to signify that you have an excited state to the ground state is given by this one here. So you have your X star decays to your stable X plus your gamma ray. So this is a decay that happens when your nucleus is very excited or in excited state, and then it decays the gamma ray in order to transition to some lower energy state. The gamma rays are normally emitted soon after the nucleus is created in an excited state. Sometimes sometimes selection rules prohibit a certain transition, and the energy state may live for a long time. Those affected by the selection rule are called your isomers or your isomeric states, and these are denoted by a small m for metastable. So for example, you have the spin 9 state of your bismuth 210M. Again, your M here tells you that this is a metastable state at 0.271 mega electron volt. Excitation energy does not gamma decay because of the large spin difference transition. And even though for niobium 93M, this is another example of prohibited decay to the ground state, uh, the probability of occurring is small and it does gamma decay. Your gamma decay here in the figure, you have your unstable nucleus A star. It decays to a stable nucleus A by emitting a gamma photon or your gamma ray. Your gamma decay actually accompanies your beta or your alpha decays, and this is an isomer transition. The process of the excitation of a metastable state is given by this equation here. You have your X star that decays to your stable nucleus X plus your emitted gamma ray or your gamma photon. There is actually a competing reaction to your gamma decay, and we call this one as your internal conversion. So in your internal conversion, the excitation energy is transferred from the nucleus to an orbital electron, ejecting it from the atom. It, fo it followed It is followed by the characteristic photon emission and OG electron emission after the vacancy is filled. So this is your internal conversion equation. And where here your X star is the excited state of the nucleus, your X plus is the singly ionized state of atom X, and then your electron, your internal conversion electron. And this is the summary of your decay modes in your nuclei chart. So we have here your decay modes, the characteristic of your parent nuclide, and then the change in Z, and then the change in your N. For your alpha decay, this usually happens for heavy nuclides. So there's a -2 change in Z and then -2 change in N. For your beta, you have neutrons. So you have +1 change in Z and then -1 change in N. And your positron, you have excess in protons. So -1 change in Z, +1 change in N. For your electron capture, you have your excess protons, and you have your -1 change in Z, +1 change in N. For your gamma decay, there is excess energy, There's no change in your N and Z. And then for the competing of your gamma decay, which is the internal conversion, you have still excess energy characteristic of your parent nuclide, and no change in Z and N. As you can see here, this beta that you are referring to is your beta minus decay, and this positron decay is your beta plus decay. Now, let's discuss about our sources of radiation by discussing the background radiation. Your background radiation is the ionizing radiation emitted from a variety of natural and artificial radiation sources. So our sources are the following. You have your cosmic and solar radiation. You have your terrestrial norm meaning your naturally occurring radioactive materials. And then we have your atmospheric norm, and then your man-made radiation. This is a pie chart of our sources of background radiation, which is mainly comprised of your radon, and then next you have your internal sources, your medical sources, and then your terrestrial, and then your cosmic, and then other you have your consumer products, and then your other sources. These are our sources of radiation exposure. The greatest part of your pie is your background radiation, wherein we have your radon and then your thoron, 37%, and then you have from space, 5%. And um, from your medical part, you have your computer tomography, 24%, and then your nuclear medicine, which is around 12%. So here shows our sources of radiation. Many are also from the industrial source, occupational source, and then consumer sources. Okay, and that's it for this lesson.